We know that solar panels provide little electricity in winter due to a lot of cloudy days and snow, but this video will show how similar solar heaters can overcome this shortcoming, and our solar stations can work just as well in winter as they do in summer, in addition to our ability to generate electricity at night, on cloudy days and other advantages over solar panels. I am quick to point out that these mirrors focus solar radiation which produces very cheap steam, and I'm testing different types of solar heaters to find the type that will give us solar thermal energy at the cost of half a cent per kilowatt hour, and it is about 10 times cheaper than the cost of heat from natural gas. These cheap solar heaters should replace these very expensive mirror structures whose long rows form such large solar power plants covering an area of several square kilometers, and forecasts for the development of similar mirror power plants can be like this, where now the annual turnover is several $billion, but it could be tens of billions of dollars in a few years. These expensive solar heaters have mirrors that focus the solar radiation into this receiver, where the radiation heats thermal oil up to 400 degrees Celsius. The hot oil is transported to the center of the power plant, where a proportion of the thermal energy of the oil produces steam for a turbine with an electric generator, and the rest of the energy of the oil heats tens of thousands of tons of substance inside these heat storages to a temperature of almost 400 degrees, and this thermal energy produces steam for the same turbine during 6 or 10 or 15 hours in the evening and at night. It is obvious that an increase in the volume of our heat storages by several times will increase the reserve of their energy for several tens of hours of operation of the same turbine, which will now receive the energy from the storages not only during the coming night, but also for several cloudy days in a row. But let's additionally increase the volume of our heat storages by several tens of times, and the substance of these heat storages will be heated during the summer months, and then they will store the thermal energy for several months to provide the energy to the turbine during the cloudy winter months. Thus, our solar power plants become independent of weather and seasons, and they will be able to produce electricity in winter as much as in summer. This is the first example of gigantic heat storage for transferring large amounts of energy from summer to winter. It was built 15 years ago, and the heat storage is the soil inside these dimensions, and let's see how it is operated in this town in the southwest of Canada.
The town has a large number of these solar collectors. The collectors convert solar radiation into heating a heat transfer fluid which goes through pipes inside these boreholes and therefore transfers its thermal energy to the surrounding soil. This heating of the soil occurs during the summer months, and the soil temperature reaches 80 degrees Celsius in September. This thermal energy is stored for several months, and then it goes to the district heating of the houses in this town. That is why usually 100% of the heating needs of these houses are covered by solar energy from that soil and from the solar collectors, although sometimes, but very rarely, they use natural gas. Now I am showing how the Canadians quickly build their heat storage during several months. Unfortunately, the Canadian heat storage loses a lot of thermal energy through the soil and a little energy through this thermal insulation, which consists of a layer of this material 20 cm thick and a layer of soil about 1 meter thick, and now I am showing a green loam that covers the heat storage. These heat losses take about 50% of the useful heat during the 6 months of autumn and winter, but these percentages can be drastically reduced. For example, we know that increasing the volume of a heat storage by 1000 times reduces those percentages by about 10 times. Approximately this large heat storages for several million cubic meters of soil is required for our solar power plants to transfer a huge amount of thermal energy from summer to winter. But our solar power plants will heat the soil up to several hundred degrees, and therefore we have to make some small changes to this Canadian heat storage. For example, the Canadians use these plastic pipes in those boreholes, while we should use metal pipes. In addition, our large heat storages may have similar problems due to groundwater, and let's look at other types of heat storages which do not require drilling expensive boreholes up to several hundred meters deep. Perhaps someone saw the interview of these young Finnish people, and they talked about the idea of combining our heat storage and an abandoned quarry that spoils the landscape and causes the death of children. When we build our heat storage, we can fill our quarry not only with millions of tons of soil, but also with cheap waste from mining and from various factories and plants. It is obvious that filling our quarry with soil or waste is accompanied by laying of pipes for the heat transfer fluid, and the laying is noticeably cheaper than drilling those boreholes. The next idea for our heat storage is a mountain, which we will heat in the summer to a temperature of several hundred degrees. It is desirable that it be a dirt mountain, because we have to drill a lot of horizontal boreholes for those pipes for the heat transfer fluid. But it is obvious that such a hill may be cheaper to make from the surrounding soil, because building an artificial mountain from soil or waste is accompanied by laying of the pipes instead of drilling the expensive boreholes. The volume of our artificial mountain will be close to these well-known pyramids, several million cubic meters, but the height will be several times less. And now I am showing some interesting shapes of our heat storage. This formula leads us to this cost of our solar electricity, 5 cents per kilowatt hour, and this cost of our electricity wins the competition against thermal and nuclear power plants. Here we see the cost of our cheap thermal solar energy, half a cent per kilowatt hour, and this value requires such a low cost of our heat storage, $8 per ton of soil or waste. But these are requirements for a sunny desert climate, and other regions may have different requirements due to less sunny winters and opportunities to improve our profitability with revenue from sales of heat for city district heating or greenhouse heating. Let's take a closer look at the operation of this artificial mountain made from soil that will heat up to several hundred degrees. Its lower thermal insulation is this layer of soil between our mountain and groundwater, but we can increase its thickness by using this lower part of our mountain as thermal insulation rather than as heat storage. The upper thermal insulation of our heat storage is this layer of soil with a thickness of approximately 5 or 10 meters. The upper insulation can consist of several layers of different materials, and for example now I show the layers of materials over that Canadian heat storage, including the layer of soil of this green lawn. Another interesting idea is to place a large greenhouse here, and especially interesting is the location of the greenhouse here on the southern slope of our mountain. It is obvious that such greenhouses can be heated by the heat leakage through the thermal insulation of our artificial mountain. In addition, the greenhouses will be waterproofing against rainwater, and an additional method to reduce the heat leakage, because this air temperature will be several tens of degrees higher. The next interesting idea is used by both these Finns and those Canadians, and it refers to these pipes for the heat transfer fluid that exchanges thermal energy with the soil of our heat storage. These pipes should be located both in the center of our heat storage and on its periphery. We should strive to take thermal energy from the soil primarily through these peripheral pipes, because this method leads to a decrease in the temperature of the soil on the periphery of our artificial mountain, and therefore those heat losses are reduced. Of course, I made calculations of these heat losses, and it turned out that our mountain with a volume of soil equal to 4 volumes of the pyramid of Cheops, and such dimensions loses this much thermal energy through its bottom for 12 months of 1 year. These heat losses through the sides of the mountain have such a value for 12 months, but this mountain stores this amount of thermal energy, and it is almost 7 times more than the sum of all those annual heat losses. Everyone can check my calculation given that this thermal insulation has a thickness of 10 meters of soil. This thickness to groundwater is 10 meters too, and this is the temperature of the soil in the center and on the periphery of our mountain. Of course, here we can add layers of thermal insulation with a total thickness of several meters, and all the soil of this mountain will be our heat storage. It must be cheap thermal insulation with such a total construction cost, for example, mineral wool, foam insulation, agricultural waste, and possibly a thin inner layer of solid heat insulator plates. Let's look at my calculation of the heat losses for a mountain with volume of 2 pyramids of Cheops and such dimensions. This is the heat losses for 12 months, and this is how much this mountain stores thermal energy, and it is almost 8 times more than the sum of these annual heat losses. This thermal insulation has a thickness of 2 meters and this coefficient of heat conductivity, and this is the temperature of the soil in the center and on the periphery of our mountain. I remind you that the temperature of the thermal oil at the inlet of these expensive solar heaters is about 300 degrees Celsius, but here the solar radiation heats up the oil and therefore it leaves with a temperature of almost 400 degrees. Then this hot oil transfers its thermal energy to heat storages, and therefore its temperature decreases again to 300 degrees, and it returns to the solar heaters for the next heating. A similar transfer of the thermal energy of the oil to the soil of our mountain occurs in such a way that first the oil goes through its central pipes and then through the peripheral pipes. In other words, the hot oil moves from hotter pipes to colder pipes. It was a situation for sunny weather, but such partially sunny weather can reduce the operating temperature of our solar heaters to less than 300 degrees, and therefore the movement of hot oil bypasses the central pipes of our heat storage. Morning or evening can reduce the operating temperature below 200 degrees Celsius, and therefore the oil moves only through the peripheral pipes. So, our solar heaters will give us the thermal energy in any sunny weather and any daylight hours, but only if their heating temperature is higher than the oil mobility temperature. We know that steam turbines are powered by thermal energy of different temperatures, and initially low temperatures heat water. Then the higher temperatures evaporate the water, and then the thermal energy of the highest temperatures will heat the steam. In addition, some turbines expand the high temperatures to additionally heat the steam that has already passed through part of the turbine. So, the hot oil can circulate through all the pipes of our heat storage and take thermal energy of different temperatures for different stages of heating water and steam of our turbine. But when the sun is shining, the hot oil comes from our solar heaters, and the proportion of the oil transfers its thermal energy of different temperatures to our turbine, and the remains of the oil transfer its energy to our heat storage. We could notice a disadvantage such that the winter months will have a deficit of high temperature thermal energy of about 300 degrees, in contrast to the fact that for the summer months these low temperatures will be a deficit. I propose to try to solve this problem by using two turbines, but for different operating temperatures, and usually both turbines will work simultaneously, but sometimes one of them will stop temporarily. In winter, this turbine is constantly operated, and this turbine will operate periodically during the presence of thermal energy of 300 degrees, but during the summer months it will be the opposite. Perhaps it would make sense to add this third turbine, which may be required to eliminate excess thermal energy of low temperatures, especially in winter. Usually, engineers will advise using here not steam turbines, but heat engines of this type or some other types. But I repeat that these were only my ideas, and perhaps we will find better ways to solve that problem. We know that this solar station in Denmark heats thermal oil to over 300 degrees Celsius. This energy is spent on the simultaneous production of both electricity and thermal energy to heat water for district heating of the town. Engineers call this simultaneous production of electricity and heat by this term, and the heat can be stored not only to cities for their district heating, but also for heating large greenhouses and for industrial processes of various plants and factories. These cases of simultaneous generation of our solar electricity and heat will be analyzed in my future videos, and now I will show another opportunity for the heat sales. For example, we understand that the thermal energy from these pipes can heat water to approximately 100 degrees Celsius for city district heating. Heating a greenhouse can be done at a lower temperature, several tens of degrees Celsius, and therefore we can use the following idea. We remember that our artificial mountain is surrounded by this soil thermal insulation, inside which we can install these additional pipes for circulating and heating the water of the greenhouse heating system. It is interesting that the heat extraction through these pipes reduces the temperature of this thermal insulation. This phenomenon leads to a decrease in these heat losses to the outside of our heat storage, although it increases these heat flows from our artificial mountain into the thermal insulation. Plants and factories may require thermal energy of different temperatures, and for example, the thermal oil of these pipes can be used to generate large amount of steam for industrial processes of a factory. These pipes give higher temperatures in the form of hot thermal oil that circulates between our heat storage and a factory. It is also obvious that these pipes inside the thermal insulation can heat water for the hot water supply of a factory and for its industrial processes with a temperature of less than 100 degrees. We remember that our solar power plant will consist of these solar heaters, this turbine and this large heat storage, but perhaps it makes sense to add this small heat storage for energy reserve up to several tens of hours of the turbine operation. The possible types of this small heat storage were described in this my old video 3 months ago, and for example, it can be a heat storage in the form of a large mass of concrete with pipes for the circulation of thermal oil. When the sun is shining, the thermal oil from the solar heaters sequentially goes through different heat exchangers of the turbine and pipes of the small heat storage. In the evening and at night, a proportion of the thermal energy from the small heat storage gives the steam to the turbine, and the rest of the energy is transported by thermal oil from the small heat storage to the large heat storage. This method can reduce the number of these pipes of our large heat storage up to several times compared to the case without our small heat storage, when these pipes should receive a large thermal capacity only during the sun. Thus, in the evening and at the beginning of the night, the small heat storage transfers its thermal energy to both the turbine and the large heat storage, but the end of the night may require more complex options for the exchange of the energy of different temperatures. It is obvious that after a non-sunny day, our small heat storage is empty, and therefore the turbine takes energy only from the large heat storage.